Alright, in the last chapter we talked about local area networks. In this chapter we're going to expand that and we're going to start talking about wide area networks. Now remember, wide area network is a collection of local area networks put together. The most famous example of a large wide area network, the largest one ever, is actually the internet. So we're going to identify a variety of uses for wide area networks. We're going to explain different wide area network topologies. We're going to talk about some of the WAN technologies, including security, reliability, switching types, and some of the different medias. And we're going to talk about the way that wide area networks are connected together. And that includes a lot of things. You're going to hear a lot of new acronyms in this chapter. PSTN, which another name for is the plain old telephone network, ISDN, T-carriers, DSL, broadband, broadband over power line. That's a new one that you don't see much of here in this country, but is pretty popular in some others. And then finally some of the really high-speed connections, ATM and SONET. Alright, so to reiterate, a WAN, or wide area network, is a network traversing some distance or connecting LANs together. Remember, I told you don't get too tied down in the definition of LAN, WAN, and MAN, but basically you can think of a WAN as any network that is connected by routers. If it's gone beyond one local area network where two are connected together and there's a router, then that in some sense is a wide area network. They generally spread over vast distances, but they don't necessarily have to. And they're going to have a lot of things in common. One reason you may want to set this up to begin with is so that you can share resources, just like you would with a local area network. Another thing they have in common is they use layer 3 and higher protocols. By that we mean IP addresses and things above that on the OSI model. Any of the lower stuff, the MAC addresses, that's all local area network, and you'll see how that gets incorporated into a wide area network shortly. And then most are packet switched, and we'll talk about what that means. Alright, places they're different are in the ways that they connect. So, you know, in the last slide we showed the layer 3 and above. They're kind of similar in that they transmit data via IP address and things like that. But when you get down to the lower levels, level 1 and 2, the way that they actually connect is very different. Most wide area networks, especially in the wiring, where with a LAN it's privately owned, if the wide area network spreads over a vast distance, the wide area network is going to be connected with an ISP, an internet service provider, or a network provider of some kind. And in a lot of cases that's just the telephone company. It may be, you know, AT&T, Sprint, Verizon, Bell South, any of those. The WAN site are the geographical locations connected by the WAN. And the link is the link between the connections. Alright, more distances include the distance covered, the number of users, and the amount and speed of traffics. WANs are generally slower than LANs because LANs are local and they don't have to transmit data as far. WANs always require some sort of device that's layer 3 or higher, which is normally a router. And one thing about WANs, they cannot carry non-routable protocols. So WANs can only carry protocols that are routed. Remember back we talked in class about something called NetBEUI. That was an old Microsoft protocol that was used to connect local area networks together, or to connect computers on local area networks. That is not suitable for a WAN connection of any kind because it's not routable. So that protocol, without doing very special things that involve putting it inside other protocols, can actually be routed out onto a network. Here they're just giving you an example of a LAN and a WAN. You know, on the side over here we've got a local area network connected to a couple of file servers and out to the internet. And over here a WAN, they're showing that it's much larger. They've got several different cities. Alright, so some of the different types of WANs are somewhat similar to things that you're going to have seen before in dealing with local area networks. A bus topology LAN, for example. Each site is connected serially to two sites. The network site is dependent on every other site to transmit and receive traffic. Different locations connect to each other through point-to-point links. This is best for small organizations that have dedicated circuits. The drawback to a bus WAN is that it's not very scalable. If you've only got 3 or 4 places to connect together, this is fine. But if it gets much larger than that, then it gets to be a real headache because everything's dependent on everything else. And here's an example. We've got some buildings. The first 2 are connected with a DSL link, the second 2 by a T1, and the third one over here by a T3. Now the plus to this is that it's easy to set up. The minus is that for the network to be maintained and to be operable, all of these connections have to be up. If this T1 between Madison and Watertown, for example, goes down, then the entire network is offline because there wouldn't be a way for like Madison to talk to Columbus. In a star WAN, you have a central connection point and separate routes between the sites. The advantage of this is that a single connection, with the exception of where your network operations center is, which you'll hear me use the term NOC occasionally. And NOC stands for Network Operations Center. That's your main point in a star network. With the exception of the NOC, if one piece of this network goes down, then the rest of it would stay up. It is easier to expand this. But here again, the drawback, just like I said, if the NOC goes down, the whole thing would go down. And in their graphic here, 2110 Main Street in Madison is going to be the NOC. We've got a T3 connection and a couple of T1s. But in this case, if 1 South Oak Street in Madison goes down, the rest of the network stays up. Obviously, 1 South Oak Street won't be able to communicate with anybody, but the rest of the network will still be able to communicate. In a mesh network, you have many sites that are connected to each other. The data travels from origin to destination. Routers can redirect the data easily and quickly. This is the most fault tolerant of all the types. It is, of course, also the most expensive. In a full mesh, every site is connected to every other site. That means if there are 5 connections, then each connection will be connected to the other 4 stations. The drawback of that, of course, is cost, because that means you've got way more extra links and things. What's way more common is a partial mesh. And in a partial mesh, some connections are doubled and some are not. And here we've got a full mesh. You see, if you only have 4 buildings, maybe not so bad, because you connect every building to every other building. And in this case, when a connection goes down, the data can just be routed around the downed connection. What is way more common, though, is this partial mesh you see over here on the other side. And in it, you have backup links for connections that are critical. Like, for example, we have the T3 that goes through Madison from Detroit to Dubach. Well, that would be the faster connection that would probably be used most of the time. But if this connection between Detroit and Madison were to be lost, this T3, this DSL connection could still be used. And because of the way that routing works, if either of these T3s went down but not both of them, this network would still be fully functional, because data will just be routed around the connection that's down. A tiered connection is one where the sites are connected in star or rings and they're interconnected at different layers. This allows for a pretty flexible network because you've got many variations. But things you have to consider about this are usage patterns, the growth potential, and the geography of the network. And here they're showing a tiered topology. And in their example, they've got a couple of T3 main connections, and then some T1 connections to some other offices. The main time that you see something like this used is if there are small offices in a city, but there's a main office as well. Like if you have 3 main offices in 3 different cities, but then some little sub-offices. You can connect your main offices with your faster connections, then connect those sub-offices into the main office for that city, and then connect the 3 cities together. So earlier I mentioned the PSTN, and that is the Public Switch Telephone Network. That is the plain analog telephone system that some of you may have in your house. You pick up the phone and get a dial tone. It's also called the POT sometime. And that just stands for plain old telephone service. The telephone system, it encompasses the entire telephone system. And originally the entire system was analog. Nowadays that is changing. A lot of it is digital. Maybe not actually to the home for a lot of people, but the network itself is mostly digital now. And in the old days, to get on a connection on the plain telephone network, what you would have to do is use a device called a modem. And I'll talk more about a modem later, but it basically converts the signal the computer makes in digital to something analog that can be sent over the telephone. Then on the other end, it's converted back into digital so that the computer on the other end can understand it. So here again, the PSTN cannot handle digital networks. It requires a modem. Signals travel on this system between modems over the carrier's network. And this includes what's called a CO and a remote switching facility. And the CO is where the telephone company terminates the lines. The switches calls between different locations, that happens at the CO. Now in the old days, the CO was actually one big building in a city, and all of the wires ran back into that one building, and everything was switched there to go back out. In Shreveport, the central office used to be downtown, and from my understanding, now I don't know a lot about the history, but all the phone lines in all of Shreveport used to run into that building. And that building had just tons and tons and tons of wire that came in because there were 2 wires coming in for every single telephone customer. And all of the equipment took up that big building downtown in order to switch between phone calls. It's the building there, I believe that's on Marshall Street. It's got no windows, and if you look at the front of it, there's a picture of a painting on it. But nowadays, the central office in a lot of cases is not actually an office anymore. Since we're switching to digital between connections on the telephone network, the central office might be one of those junction boxes that you see on the side of the road. And that's where the lines all come in from analog, and they're switched into digital there, so that fiber and other things can be run from there back to central offices. So basically, Bell South has that big, huge office downtown that had all of this equipment in it, and now it's probably got nothing more than just a server in it that's doing what all of the mechanical equipment for individual wires used to do. Alright, so some other terminology to know. The local loop is also called the last mile, and that is the portion that connects the residents to the nearest CO. It may be digital or analog. For most people, that is still analog. If you have a digital local loop, you may have something that's called like fiber to the home or fiber to the premises. We don't have that in Shreveport yet, but if you live in Dallas, or if you visit Dallas, Houston, some big cities, they have a service from Verizon called Fios, and that's what that is. And fiber to the home has a lot of advantages because not only is it a pure digital signal, but they can run more than just one service on that fiber. If you get the Fios service, for example, from Verizon, it's going to have your telephone, your TV, and your internet all on one wire. And then the passive optical network is the carrier's fiber optic cabling to connect the endpoints. So here we're showing the example of how a long-distance dial-up connection works. First, you have an analog signal over the local loop that would reach the CO. At the CO, it's digitized, so it's a digital signal running to a regional office. From the regional office, it's going to go into the cloud, which is simply the connections between different regional offices until it reaches the area that the phone call is trying to go to. Then it would hit the regional office for that area. It would be a digital signal again until it reaches the CO. And then on here they show it going a digital signal again, but if it were going to another house, it would trade off here again to be an analog signal for the last mile, which would be the last local loop till the end point of the call. Here they're showing the portion called the local loop. So an optical line terminal is a single endpoint at the carrier's central office. There are devices with multiple optical ports here, and an optical network unit distributes the signal to multiple endpoints using fiber. Now, most of the new stuff is fiber, but it could be copper if it's an old system, or it could be coaxial cable. When they first started moving away from copper, they went to coax, and then fiber came out, and fiber is much faster, so everything moved to fiber. Alright, here we're showing an example of a passive optical network. And you see they've got fiber to the home that's going to be running to one of these ONU units. It's an optical network unit. From there it's fiber into what would be kind of the equivalent of the CO in the old system. Then it's an optical line terminal that goes to other optical network units, and it's fiber optic till the endpoint. And here they also show one coax connection showing that coax could be used, or copper if you're close enough in what they call wire feet to an ONU. This is basically also kind of some of the same things that if you have DSL in your home, you have to be so close to one of these units they call a DSLAM. And we'll get more into DSL later and why that is, but basically it's because the signal can only travel so far on copper before it is unreadable. So X25 is one way of transmitting things. It's an analog packet switching technology designed for long distance. Originally it was developed in the 70s, and it was to hook mainframes to remote computers. And the speed was 64K, which is nothing now but was pretty impressive then. One place that used this a lot was banks. Banks would have a mainframe that would have all the data on them, and that mainframe would normally be in a central location, and then all of the remote offices, all the remote banks would have one of these dial-in or these X25 connections to connect back up to their mainframe to see the data on the customers. In 1992 they updated the X25, and the new standard is 2.048 megabits. One thing about X25 is that it verifies the transmission at every node. That means that it ensures data reliability. It's very, very, very reliable. But the trade-off, as you've seen in other things we've talked about with all this verification, is that it's slow. This makes it not very good for time-sensitive applications. Alright, so the updated X25 is digital. The protocol operates at the data link layer. That means, remember, it's layer 2. It supports multiple network and transport layer protocols. Both X25 and Frame Relay perform error checking. Frame Relay, however, has no reliable data delivery guarantee. X25 fixes or retransmits the errors. As far as speed, for X25, 64K to 45 megs is about the fastest you can get. Frame Relay, the customer would choose the speed that they wanted to pay for. Alright, in X25 and Frame Relay, we have what's called a PVC, and that is an individual link that is not dedicated. Basically, this is what in the T1 world you would call a frac line, a fractional line. And you share the bandwidth with other users. That also makes the cost cheaper because you're not dedicating that bandwidth from the phone company. And what you do with this, your contract will specify what's called a CIR, I can't talk today, a committed information rate. And what that is that is the minimum bandwidth that they're going to guarantee that you get. So you may buy, 1 meg of bandwidth, and at times you may get 2, 3, or even higher, but they're only going to guarantee that it'll come through at 1 megabit. Here's an example showing Frame Relay, and basically you're going to have equipment that connects you to the Frame Relay at each of the locations you have, and then the Frame Relay network itself is going to take care of switching and everything to get your data where it needs to go. One thing I'd like to point out on a lot of these, they show different speeds, like these T1 and T3s. Remember that on a network, when data is being transmitted, the fastest that it can go in the overall connection is the slowest connection of the entire system. So even though we have here a long-distance carrier with a T3, if ABC Business is transmitting something to this long-distance carrier, it's still only going to run at T1 speeds because T1 is the slowest of the links. Alright, so Frame Relay's least advantage is that you pay for the bandwidth you need and it's less expensive. It is a long-established standard. The disadvantage is the variability based on it being shared lines. Frame Relay and X25 can easily be upgraded to dedicated lines, though, and these are the T-carrier lines. And you've seen these in these pictures we've talked about with T1s and T3s. Those are all dedicated types of lines. And the reason it's easy to convert those is because the connectivity equipment is essentially the same. So ISDN is another type of connection, and it is a standard for transmitting digital data over the POTS, or the plain old telephone network. This got popular in the 90s, and they actually started rolling this out as a home service. You could get ISDN and it gave you faster internet at your home. And it was still a dial-up connection of sorts. You still dialed in to make it work. But what happened is that cable modems and DSL and these other technologies that are dedicated and faster came along and ended up being a little bit cheaper. So ISDN kind of got dumped from the home scene. It's still used a lot for backup connections, though. This operates at the physical, the data link, and the transport layers. So ISDN is concerned with signaling, flow control, error detection, and correction. And it's usually dial-up, but there can be a dedicated signal system for ISDN. Alright, so the way ISDN works is that you have 2 channels and a data channel. And what we mean by that is that you have 2 B channels and 1 D channel. And the way that works is that the B channel is the bearer, and that is circuit switching for voice, video, or audio. And the D channel is called the data channel, but it doesn't necessarily mean that just data has to go on the D channel. The D channel is the packet switching information to actually make the system work. And then there are two speeds or types for ISDN, a BRI and a PRI. BRI is a basic rate, and PRI is a primary rate. So here with a BRI, you have two B channels and one D channel. The B channels are treated as separate connections. That means they can carry voice or data. And the way that you get the speed out of ISDN is to bond those two channels together. And what bonding means is half the data goes down one channel and half down the other. It's essentially the same as with the old analog phone system. What you could do if you needed a faster connection is get two dedicated phone lines and connect both of them to do two dedicated phone lines at the other end. And you could set your data so that it would go out both of them at the same time, so you could get it faster. A PRI is 23 B channels and 1 D channel. A PRI's maximum throughput is 1.544 megabits. And you'll see in a little while that is a number that's very close to a T carrier line. And that is why some, ISDN got to be popular for business. You could get the same speed you could get out of a T carrier. And here they're showing an example of a BRI link. Here they're showing a much larger one, a PRI link. And that brings us to our T carriers. T carriers, this is a physical layer connection. And the way that a T carrier works is that it's based on a process called time division multiplexing. And it works over two wire pairs. So with a T1, you could have a telephone wire, you could use fiber optic, or there are some wireless T carriers. And T carriers used to be the standard in connections because they were one of the fastest things you could get, and they were very reliable. And you'll see the speeds here in a minute, a T3, T1. And then earlier you heard me talk about a fractional or a frac. That's where you buy part of a T1 or part of a T3. So here we've got our speeds, and I want to point out earlier I talked about T1 and the 64 channels for the PRI on ISDN. And notice here they're the exact same speed, 1.544 megabits. So a T1 is the 1.5, a T1C 3.152. T2s did exist. You didn't hear very much about them. Usually people went from a T1 up to a fractional T3 or a frac T3, which meant they bought part of this bandwidth. And if they needed it all, then they got a full T3, which is pretty expensive. But you see here a T3 is like 28 T1s put together, or 672 individual channels. So a T3 could handle 672 actual analog telephone calls at one time. And then they do go beyond that, a T4 and a T5, and they're going up, 274 and 400 megabits. So a T1 here, 24 voice or data channels. A T3, 672. The T carrier speed is dependent on the signal level. Earlier, you saw the numbers next to it. A DS0, a digital signal level 0, is one data or one voice channel. So T1's uses are mainly for connecting branch offices to carriers, connect telephone company COs. They say ISPs on here. A T1's not going to use an ISP anymore. That's not going to be enough. A T3 is going to provide 28 more times the throughput of a T1 for really data-intensive things, but it's also going to be very expensive. The cost of these vary by region. And here they show a fractional T1. You could get a fractional T1 if you didn't need the full T1 speed, and it would be cheaper than a full T1. And you could do a frac on any of those. I just mentioned a frac T3, but you could get a frac T5 if you needed something faster than a 4, but not quite as fast as a 5. So T carriers require connectivity hardware at the customer site and the switching facility. It's purchased or leased. In most cases, it's leased, and it can't be used with other WAN transmission methods. This is special equipment that's only used in T carriers. The T carrier line requires different media, which makes it throughput dependent. So T carriers could use plain telephone wire, UTP or STP. Remember, that's unshielded twisted pair or shielded twisted pair. Normally, shielded twisted pair was used. And again, it matters how close to the main office you are as to whether this will work or not. Preferred wiring is coaxial cable or fiber optic because that would be faster. Or you can do microwave wireless T carriers. T1s using shielded twisted pair require a repeater every 6,000 wire feet. So this can get to be expensive if you're not very close to a CO where it can be converted over. And then if you have multiple Ts or a T3, you're probably going to have fiber optic cabling. Though I would like to point out you can get a T3 that would run on coax. They're not very common, but it is possible. So here they're showing the connections in a typical T carrier wire. T uses an RJ48 connector, which is just a little bit bigger type connection than your RJ45 that you use to connect a local area network connection. And here, if you're going to build a crossover cable, you won't need to know the pinouts for the test. Just kind of be aware of them. If you get into doing this stuff for a living, you know, you'll memorize some of these because you'll be making cables a lot. So the equipment required for a T carrier is a CSU and a DSU, and it's a channel service unit or a data service unit. And these are actually two separate devices, but they're usually combined into one device. They can be two separate ones, but again, you know, in the network world now, we're seeing a lot of things that are built together. I've mentioned in class a lot of you have probably a wireless router at home. It's actually two devices or three. It may be a switch, a router, and an access point, but they've started putting them all into one device to make it easier. Well, on this CSU DSU, you would have that would have an interface card that could be changed out based on the type of media. The CSU provides the digital signal termination and ensures the connection integrity. The DSU converts the T carrier frames into something the LAN can read. So the DSU turns it into data that can be local and then takes that and turns it back into stuff for the T network. It connects the T carrier lines with the terminating equipment, and that is done by incorporating a multiplexer. A smart jack terminates the T carrier wire pairs, and this is the point that's known as the demarc. And a demarc is the point where, remember that the phone company's equipment ends and your personal equipment starts. So if you're on one side of the demarc, the equipment's the responsibility of your phone company or your ISP. The other side of the demarc is the equipment that's your responsibility. They say it's inside or outside a building. These are usually inside, but they do have special boxes they can put them in to make them outside. Here we've got an example. We've got a T carrier in the middle, a couple of smart jacks, and then a CSU, DSU, and equipment on both sides. So we've created a network, a wide area network that would connect terminal equipment over here to terminal equipment over here using a T carrier in the middle. So the multiplexer separates the combined channels for incoming, and on outgoing it combines the LAN signals. The terminal equipment is going to include switches and routers, usually a layer 3 or higher switch. These will accept incoming CSU DSU signals, translate them into network layer, which is layer 3 protocols, and allows you to direct data to the destination. Remember layer 3, this means that it's routable. The CSU-DSU might be integrated with a router or a switch. Again, this goes back to the fact that they're making a lot of this equipment that gets combined together. The last CSU-DSU that I dealt with was actually built into part of a switch. We had one of these at the juvenile court, and it was our connection to run background checks on the FBI. And it was a Cisco router that had a CSU-DSU card in it that was connected to a T1 line that ran down to Baton Rouge. And it also had a modem in it with an extra phone line, and that modem was the backup link. So if the T1 failed, it would dial up a number on the modem to make that connection. So here they're showing an example of a carrier connecting through a router. You've got the internet out here, our T carrier to our smart jack, a router with a CSU-DSU and a multiplexer. The multiplexer side would run over here to the telephone equipment for part of the T1 to be phone lines. The data part from the CSU-DSU would run to your switch that would then connect to your computers. So a type of connection that is pretty common for home users now is DSL, or digital subscriber line. DSL runs over the plain old telephone network, and it directly competes with ISDN and T1 services. It does require repeaters for longer distances, but it's best suited for the local loop part of a network. It supports multiple data and voice over a single line. And the way this works is it uses frequencies that are higher, that are inaudible to the human ear. This is also why if you have DSL and you have phone lines, a phone line on it as well, or voice line, you have to plug in those filters, because those filters that run to your phone are what actually filter out the higher signal to make sure that you don't hear it. And DSL uses some advanced data modulation techniques. It alters the carrier signals in multiple ways so that it can put more than one piece of data on the line at one time. There are tons of different types of DSL. And when you see it written as just XDSL, that refers to all of the DSL varieties. They listed some here. There are tons more than that now. And it varies based on where you live or what type of standards being used. It also varies based on phone company in some cases. But there are two major categories, asymmetrical and symmetrical. And symmetrical means you've got the same uplink and downlink, or upstream and downstream as they say it here, speed. Asymmetrical is what most people have, and that means your downstream is faster than your upstream. So data from the carrier switching facility to the customer is faster than data going from the customer back to the switching facility. And for home users, that's fine, because for the most part, you're downloading way more information than you're uploading. So here they're showing that the rates may differ, just exactly as I said. Asymmetrical, more throughput in one direction. The downstream is higher than the upstream. Symmetrical is better if you're uploading a whole lot of data. HDSL, SDSL, and SHDSL are symmetrical examples. So here are some of the different types, and you see each of them have some different advantages. The maximum speed you can get out of them, but the distance they have to be in feet from what we said earlier is a DSLAM, and I'll get into that in a minute. But that's the connection for DSL. Here, for example, if it's HDSL or HDSL2, it can be up to 18,000 wire feet away, so that'll go a lot further than VDSL down here. But you see, HDSL can only do at most 2.048 megabits. Where VDSL, if I'm within 4,500 feet of a DSLAM, I may be able to get up to 51.8 megs over the connection. So ADSL, a common example, is a home computer. It transmits data through a DSL modem. They can be internal or external. Most are external. The splitter separates the voice and the data signals, and they may connect to a switch or a router. Here's an example of a typical home user's connection. You've got a DSL modem with a phone and a computer run to a splitter. Splitter's going to run into a connection on the plain telephone network that will hit a DSLAM. This is the CO facility here they're showing. And now remember, the CO may not actually be a central office. This DSLAM is most likely in one of those silver boxes somewhere outside of your house. And then that DSLAM here they show connecting directly to the internet. But usually those DSLAMs are going to run to some sort of central office where there's going to be a much faster connection that's going to run on out. So you're going to have a CO that runs to a like a master CO. So DSL competes with T1, ISDN, and the big one, broadband cable. The DSL installation is pretty easy. You do have some hardware. It's slightly less than ISDN in price. It's significantly less than a T1. The drawbacks are that the throughput is usually lower than broadband cable. But in lots of places, DSL may be your only option for high-speed connections. So broadband cable is generally what most people have. At this point, I would normally ask this to the class, and usually all but a few people hold up their hands. Broadband is usually a better connection if it's available to you. You're using the cable company's coaxial cable to connect to this. The theoretical maximum with the technology we have right now is 150 megs downstream or 10 upstream. But in reality, what most people get is 10 to 15 down and 2 up. The transmission is throttled at the cable modem, and that is so that you don't use all of the bandwidth, because the way this actually works, it's a bus network. You and all of your neighbors on the cable system share the connection at one time. Broadband is great for downloading stuff. It's great for web surfing. Here they've got an example of a typical cable modem. It's funny here, we call it a modem because in the old days it did modulate and demodulate the transmission. In reality, though, a cable modem's really not a modem anymore, even though that term is going to stick because we've gotten so used to it. The cable system is almost completely digital everywhere in the United States now. So what that device does is actually just changes from one type of digital to another type of digital. These operate at the physical and the data link layer. And they normally connect to a connectivity device. So this is going to go to a router or a wireless access point or something before it goes to your computer. So the infrastructure for broadband cable to work is HFC, or hybrid fiber coax. They say that it's an expensive fiber link supporting high frequencies. That price has dropped, significantly, and it connects the cable company's offices to the node. The cable drop is the node where it actually connects to the customer, either in a business or to your house. The cable drop is the part that runs to your house. In all of Shreveport, that's a piece of coax. We don't have fiber connections. And that runs to what's called the head end. And the head end is where the cable system connects out onto an internet. So the thing about cable is you share the same local line or throughput with your neighbors. Here they're showing an example. We have the cable drops that are going to run to a distribution hub. The distribution hub will run to other distro hubs. It'll finally hit a head end, and the head end is where it'll connect out to the internet. And here they show it connected as a ring connection. This HFC is the hybrid fiber cable connections. So another technology that is gaining a lot of popularity in other countries is called broadband over power line. And this started, it's been around for a little while, roughly around 2000. The advantages are that it uses the power line cables that are already run everywhere to transmit data. And this is a way to get to very remote users, because even people that live out in the middle of nowhere that maybe can't get DSL because they're too far from a DSLAM unit on their wire feet, or that live out so far that they won't run cable out there because it's not cost effective, might be able to get internet this way, because even if they live out in the boonies, they've probably got power. Roadblocks to broadband over power line, though, there are infrastructures that have to be installed for this to work. There's more noise than DSL or cable. The signals sometimes interfere with amateur radio. And a lot of the telecommunication groups are opposing it because they know that it could be a threat to them. A lot of money goes into lobbying against this by companies like Verizon and AT&T and others that have an interest in it. So ATM is another type of connection. ATM stands for asynchronous transfer mode, and it works at the data link layer. It is an asynchronous communication method, and what that means is that the nodes don't conform to predetermined schemes. Each character is transmitted on ATM with a start and a stop bit. And it specifies the framing technique that is used. One thing about ATM is, though, even though it's fast, it has a fixed packet size of 48 bytes plus a 5-byte header. And because of that fixed packet size, ATM can end up with a lot of waste. If you're using a protocol like Telnet that only transmits one character at a time, you're still going to have a 48 byte plus a 5-byte header. Each one is just going to have one single letter in it, so there's a lot of waste. The small packet size does require more overhead, but the cell efficiency compensates for that loss. ATM relies on virtual circuits. It is a packet switching technology, but the virtual circuit created provides the switching advantages. And ATM does allow for QoS, which means that you can prioritize packets if there's voice packets or other packets you want to make sure get on your network quicker. ATM is compatible as far as compatibility. It is faster than some of the other things, but the cells support multiple higher layer protocols. So even though the packet sizes are small, other ones can be encapsulated into an ATM packet to be sent out on an ATM network. And you also have a special type of ATM called LAN, or LAN emulation. And what that allows you to do is to integrate an ATM network with an Ethernet network. They mention token ring here, but you don't see very many traditional token ring networks on ATM. What you do see are ATM rings, but Ethernet can be encapsulated into packets that can go out on the ATM network. And what encapsulation means is that you take the entire packet. As we saw earlier, we've looked at what an Ethernet packet looks like on a network. You take that whole packet and you put an ATM header around it. So you break it up and send that over the ATM, and when it gets to the other end, the LAN emulation takes the cells and puts the Ethernet packet back together from the data and puts it out on the network. Now, the reason that ATM is popular is the speed. You can get up to 622 megabits. You can get faster than that now, but it is a relatively expensive technology. SONET is another type of network, and a SONET is a synchronous optical network. And the way that SONET works, it is a very fast data transfer that uses simple link additions and removals. And SONET works in a ring. I'll show you an example of a SONET ring in just a minute. But it has a very high degree of fault tolerance because you have multiple connections on your ring. It is synchronous. That means data is transmitted and received by nodes. It must conform to a timing scheme. The advantage is the interoperability of SONET. Here's an example of SONET, and we see two rings here. So if one ring is to go down, the other ring can take over and transmit the data. The double ring technology over fiber optic is what gives it the fault tolerance. SONET begins and ends at the telecommunication carrier's facility. It can connect with multiple carrier facilities, which adds additional fault tolerance, and it terminates at a multiplexer. So here they're showing SONET, even though it doesn't look like a ring, you have multiple rings coming in and out to a multiplexer that then connects to other equipment. So SONET is popular because you can get very, very fast speeds out of this. An OC1, a low-end SONET, is 51 megabits. And go all the way up here to one of these large connections, an OC768 at 39,813 megabits. So SONET connections are what you have as your major backbones on the internet because they're huge, fast connections. I would love to have one of these OC768s running in my house, but I don't see that happening anytime soon. So SONET is for large companies, and long-distance companies use this. This is what the ISPs of the ISPs actually tend to use. Telephone companies use them to connect COs together. It's best for basically audio, video, or imaging or data, but it is expensive to implement SONET. So here is a slide of some of the different WAN technologies and the typical media and throughput. You don't need to really learn the exact throughputs for all of these, but look at the WAN technologies and the medias and make sure that you understand for the certification exam what the acronyms are and what each of these mean. Make sure you understand kind of what X25 is. You don't need to know the intricate details of it, but know that that's a packet switch type of system, and know what ATM stands for. Know what XDSL means. We're referring to any of the types of DSL. So in summary, we talked about WAN. We talked about the plain old telephone connection. We talked about high-speed digitals. We talked about ISDN, T carriers, DSL, frame relay, A25, ATM X25, and we talked about broadband. Thanks for watching, everyone.